So chapter 24 is all about light in general, and when we start talking about photons and B fields and E fields oscillating, uh, we tend to lose track of the fact that that's not usually how we interact with light. Right? So we certainly can deal with light one photon at a time, but usually even a small amount of light is going to be just trillions and trillions of photons. Um, so it's useful to have a way of dealing with light in the average. And that's the field we call geometric optics. So in geometric optics, instead of treating light as a set of fields or as particles like photons, and those perspectives are also true. Instead, we think of light as heading in straight lines. So which is generally how it behaves. Light has a source, light has a direction, and on average, light heads in a straight line until it gets interrupted. The simplest kind of interruption is if it hits a surface. So if we hit a surface, there are three options for what happens to this light. It can get absorbed. If it gets absorbed, it just heats up the surface. It can get reflected. Reflected light just bounces off the surface. So just like we did for flux, we define a normal to our surface. Reflection is the easiest kind of behavior to deal with. Light comes in, light goes out, and the angle of incidence and the angle of reflection are the same. If this surface is the transition to a transparent medium, then something else can happen. Refraction can happen. So light can pass through the surface, albeit probably at a slightly different angle. And the angle that we're interested in here is the angle of refraction.
Like when light hits a prism.
Sorry, Dolan, I'm having a hard time hearing you.
Like when light hits a prism and it breaks into different colors.
Sure, but even more generally, like if light hits a glass window, or if you're underwater and you see light from above, right? So anytime light goes from one transparent medium to another transparent medium, you're going to get some refraction. So we do need to talk about one more concept to really be able to talk about refraction. And what we need to talk about is called the refractive index, or the index of refraction of a material. Quick, somebody tell me what the speed of light is. Very cute, Anthony. Very cute. Yeah, 3 times 10 to the 8 meters per second. This is the speed of light in a vacuum. It's also approximately the speed of light in air. So the air, our atmosphere for visible light, our atmosphere doesn't provide much of a barrier. So the speed of light in a vacuum, speed of light in our atmosphere, basically the same, 3 times 10 to the 8. Some materials do provide more of a barrier to light. Because they're denser than air. So if you have a solid like glass, you've got, a bunch of silicon and oxygen atoms hanging out. Light comes in. And it can't really take a straight path anymore because it's going to run into the electrons that are around one of these atoms, and it's going to get deflected this way, and then it's going to run into this atom, and it's going to get deflected this way, and then from there it's going to get deflected maybe here, which it'll get right. So light is going to ping pong off all of these pesky atoms and electrons inside the material. So the speed of light in this material is less than the speed of light in a vacuum. So our index of refraction is the amount by which it's less, right? So the index of refraction is equal to the speed of light in a vacuum divided by the speed of light in a particular material. Okay? So the effective speed of light in glass, let's say, is slower than the 3 times 10 to the 8 meters per second that it would travel in a vacuum. In fact, the index of refraction of the glass, say in your car, auto glass, it's about 1.3. So that's going to be the speed of light in the vacuum divided by the speed of light as it goes through that glass. So the speed of light in the glass is going to be 3 times 10 to the 8 divided by 1.3. So this is about 2.2 times 10 to the 8 meters per second. So I'm not going to get into the whys of my next statement too heavily. But it turns out there is a relatively simple relationship between the angle of incidence and angle of refraction as light goes through a material, and it depends on the index of refraction of the two materials. So the index of our incident media times the angle that it comes in, times the sine of the angle at which it comes in, equals the index of the refracted side times the sine of the angle it goes out at. This is also called Snell's law. named after yet another dead person. It has other fancier names if you study optics a little more, including it's also called the principle of least time, um, which is my favorite way of thinking about it. Basically, light will take whatever path that takes the shortest amount of time to get from point A to point B.
Is that BR sine theta r?
I'm sorry, could you say that one more time?
Is that BR sine theta r?
That's supposed to be an N.
N.
You guys are always dogging on my handwriting.
Well, it's not on purpose in this instance. So. Fun little thing here. Schnell in German means fast.
Yes.
Since we're talking about light. Light moves fast. So
It does.
Fast.
So it's another one of those happy accidents, like the pointing vector. Sorry, I actually misspelled this because I was thinking of the pun too much. It's not Schnell, it's just Snell.
Oh, I was going to say, is it actually an accident, or is that where the word came from?
No. It's actually the guy's name is actually Snell, but because
Okay.
German was my second language, so I always think of it as Schnell's Law and kind of chuckle to myself a little bit. But I ruined the punchline, but in this case, so stand-up career is probably not for me.
I would disagree. I'd say you're pretty funny.
Yeah, but looks aren't everything. All right. So this, in essence, is we've talked about 25.1, 2, and 3 so far. Let's take a moment and do an example problem. Reflection is super easy, right? Whatever angle it comes in at, it goes out at. The only wrinkle with reflection is if your surface isn't smooth. So if your surface is smooth, like if you have a mirror, then this is the easiest thing in the world. This is also known as specular reflection. I do not actually know the etymology on that one. Most surfaces aren't super smooth, though. They are kind of bumpy. So if you have light coming in, whatever, right, you have to draw a normal to that particular bit, and then draw an outgoing ray. And then if the light, even if the light was, physically parallel to the thing, it might come into and impact a section that causes it to have different behavior. So, in principle, if you've got a bumpy surface, even if all of your incoming light rays are parallel, your outgoing light rays might not be parallel at all, and this is called diffuse reflection. What is a little more interesting to me is refraction. Let's imagine you are standing at the edge of a pond. And there you are. And at the bottom of the pond, you see a treasure chest. So the way that you see this treasure chest is that light is bouncing off the chest and it's coming toward you. But we have to keep in mind Snell's law. So the light comes off, bounces off like so, and then we draw in a little normal, and we get some refraction going on. Whoop. Pretend I can draw straight lines. And then you see it. So if you know that, say, the depth of this pond is 3 meters, and you yourself are 2 meters tall, how far from the shore is the treasure chest? Alright, so we're going to use Snell's law to answer this question. The index of refraction of air is basically 1, right? And then the index of refraction for water is about 1 1/3. So NR is equal to 1. Ni is equal to 1.33. So our horizontal distance here, if we know the vertical distances and the angles, then we can definitely figure out that horizontal distance using a little bit of trigonometry, right? All right, so maybe we divide up in x into 2 bits. There's the underwater bit, and maybe I'll use a W. There's the bit that's in water, and the bit that's in air. And the bit that's in water isn't theta r between the light and the norm. Oh man, you are absolutely correct. Wow, all right. Yep. So tangent of theta I is going to be the part of the x that's underwater here over its height. So we can replace this part of the x with 3 times tangent theta I. And similarly for the x part, it's going to be 2 times tangent theta r. We can use Snell's law to get us a relationship between theta I and theta r, right? Specifically, the index of refraction underwater times the sine of the incident angle is going to equal the index of refraction of the air times the sine of that angle. So doing a little algebra. The incident angle is going to be the sine inverse, or the arc sine, of nr sine theta r over ni. I would like to make the point here that we actually, if we're looking at this treasure chest, we know what theta r is, right? Because what we're looking at is we're looking at where we think the treasure chest is at, right? So if we continue this ray backwards, it looks, wow, again, if I could draw straight lines, that would be extraordinarily helpful. If we backtrace that, our own estimation is that the treasure chest will be somewhere like there. So if we are looking at the thing, we can actually make an estimate of how far below the horizontal we're looking. That's going to be our theta r. So for the sake of argument here, let's just say that we appear to be looking directly at the treasure chest when we lower our eyes by 30 degrees from the horizontal. Okay, so now we can plug in all our numbers. The refractive index for the air is 1. Sine of 30 is a half. And the index of refraction in the water is, well, it's 4/3. 1.33, it's 4/3. Doing a little bit more simplification here. A half over 4/3 is the same as a half times 3/4. So it's going to be 3/8. And now we can pull out our calculators. What is the inverse sine of 3/8? Does everyone know how to use the inverse trig functions on their calculators?
$22.
How did I get theta r equal to 30 degrees? I just said it was. Yep. So incident theta will be 22 degrees. So this is what? This is something like 2.5 meters. .4. Oh, you got 2.5? We'll say approximately 2.5. Now, if we notice that that's going to be shorter than the apparent distance from the shore, right? So if we are looking straight at what we think is straight at the treasure chest, right, then we're going to think, right, so this is the apparent distance, that the vertical distance is 5, oh, no one caught my trigonometric error here. Clearly, I should put more trigonometry-based questions on the quizzes so that you can practice your trig a little more. So this shouldn't be 3 times the tangent, it should be 3 over the tangent. Right, so if we have this triangle here, there's theta I, tangent of theta I oh, no. I had it right the first time. It's been a long day. Please forgive me. Anyway, you would overestimate the distance if you thought that if you were just looking at what you thought was directly at the treasure, because then your total thing here, your total depth would be 5, 2 plus 3. So we would get tangent theta r is equal to 5 over x. So x is actually equal to 5 over tangent theta r. Oh, no. Putting that almost did exactly the same thing. Theta r is this angle with the normal. It's also down here then. So our apparent length from the shore is going to be 5 times tangent 30. This is about 2.9. All right. So trying to look directly at something that is in a different medium is hard for this reason. You got 2.4? Yeah, all right. I was doing that bit in my head, which I probably should not have done. Okay, so this is Snell's law applied. There is one more application of Snell's law that I would like to highlight. So here is our surface. We have different indices of refraction on either side. And we have a ray of light coming on up. What is the largest incident angle that you can have and still get refraction going on? So Snell's law says n1 sine theta 1 equals n2 sine theta 2. So for refraction to occur at all, the angle between the outgoing light and the normal here, this has to be less than 90 degrees. Right? Because if it was 90 degrees, then it wouldn't come out into the second material at all. It would just skate along the surface. And if it was any bigger than that, it would actually just reflect back down. Right? So that's what happens if you have... So let's see what happens at the boundary, right? What does it take to get a refracted angle of exactly 90 degrees? Well, if it is exactly 90 degrees, sine of 90 degrees is 1. So we get n1 sine theta 1 equals n2. And we can, if we know what materials we're coming from and going into, we can solve for theta. So this is sometimes called Brewster's angle. If your incident light has an incident angle any bigger than Brewster's angle, then the light doesn't refract at all, and instead it only reflects back inside. And we call this phenomenon total internal reflection. Does anyone know how your broadband internet works? So the fiber optic cables that carry the internet to our homes have an interior which is usually quartz or something like it. And then there's an air gap. So quartz has an index of refraction of about 1.6. So the Brewster's angle for your fiber optic cables that carry you the internet is 38.7 degrees. It may surprise you, but the messages that are sent down these fiber optic cables, they are sent via pulses of light. So we have a fiber optic cable here, and at the transmitting stations, the boosting stations for the internet, there are lasers that inject the light into the cables at such an angle that they will experience total internal reflection. So it is actually pulses of light experiencing this phenomenon that carries the internet to your homes. And it's not perfect. Some of this light does leak out, right? Because after many, many bounces, you lose control of the angle a little bit. So every so often there are boosting stations where this signal is read by what's called a demultiplexer. Say that 3 times fast. And then it is re-emitted into a new section of cable. Alright, that's how the internet works. At least how one small piece of it works. Any questions or comments about reflection, refraction, or anything we've talked about here? Yeah, Hanson, light is super interesting. The study of light can be very illuminating. Anthony, yeah, Brewster's angle is denoted theta b. I'm sorry you all have to field my sense of humor. Alright, so this is the end of new material for today. Next week, we're going to cover 25.6, 25.7, and all of chapter 26. So we will talk about how images are formed by lenses and mirrors, and then what we do with those images when we make, glasses, microscopes, telescopes.